Hello, hello, hello. This is Nicholas once again on this lovely Thursday afternoon, wanting to talk to you today about the notion of complex differentiability and what it means to do differential calculus with functions of a complex variable instead of just functions of a real variable. Now, the key change that we have to think about is that with a real valued function, right? It's a 2D thing, right? It's one input, one output, and it's a curve or something like this on R2. And to take the derivative, right, we only have to see if the limit on the right and on the right and on the left approach to the same value. But in the case of complex valued functions, we have an input space that's 2D and an output space that's 1D. Or it could be more, but at the very least, that's the case, right? So just our input space alone, not even drawing what the function looks like, but just the inputs that it can take in, there's a real axis and there's an imaginary axis. And this extra added dimension adds in a lot of extra nuances for complex valued functions. So, right, if I am looking at this particular point, I don't know, maybe it's 1 plus I, but it really doesn't matter what the point is. Then I want to see, can I differentiate at this point? And that's a tougher question to answer, right? Because there's an infinite amount of paths that you can approach this point from, right? You can just go straight along the imaginary axis, straight along the real axis. You can do some parabolic path along both axes. And so we have to be able to show that along all possible paths, the derivative exists and it's the same. In other words, it's unique. So let's get into some examples here. If I have f of z equals, polynomials are nice to start with, so let's consider like z cubed. And now functions of a complex variable can always be written in the form u of xy, or however many independent variables you want, plus I times v of xy. And in this case, how would we get it into that form? Well, we just would say that z is x plus iy, and then we'd cube it. So that's x cubed plus 3x squared iy plus 3, or maybe minus 3x y squared minus y cubed. And so that becomes the real part of the function is x cubed minus y cubed. And then the imaginary part is 3x squared y minus 3xy squared. And something that's really neat to notice, if you actually go on like a graphing calculator like Desmos and you graph x cubed plus y cubed equals a constant, in other words, level curves of a x cubed minus y cubed equals like C1, and 3x squared y minus 3xy squared equals a different constant C2, so in other words, level curves of that, you'll find that these are always perpendicular for all C. And that's something very interesting to notice, right? There is two different ways that you can explain that. Basically, if dy over dx is negative the partial of f with respect to x over the partial of f with respect to y in the normal case, then if you're talking about orthogonal curves, then we would have the reverse reciprocal slope, and so dy over dx is f sub y over f sub x. And so then the partial of f with respect to x dy minus the partial of f with respect to y dx equals 0. We just have to solve that differential equation, and we'll get the class of orthogonal trajectories to one of these curves. And if we do that for like this one, we'll end up getting that as our solution, or vice versa. There's also another way to explain it using conformal maps, which I'll talk about later. Now, f of z equals z cubed can be expanded like this, but now what about its derivatives? So f prime of z, hopefully as you'd expect, is just 3z squared. And we can show this through the definition of the derivative, but I think that this is so much to be expected that I'm not going to go through those details. But let's take something like f of z equals 2y plus xi, right? Because z is really z is x and y, so this notation makes sense. Now we want to check the limit as delta z goes to 0 of f of z plus delta z minus f of z all over delta z. We want to check that this limit is the same for all possible paths as delta z goes to 0, or if we're trying to show that it does not exist, we just need to show that any two paths don't give the same value. And so let's do that, right? This is very much like showing in a standard Calc 3 class that if you've got a multivariable limit that it doesn't exist just by checking two separate paths. So let's check along the real part of z as our input space, which is just x, right? In that case, we get the limit, and now it's just as delta x goes to 0, it's reduced to a 1D limit, and f of z plus delta z minus f of z, that would just become, well, maybe I'll expand it here first. As delta z goes to 0, f of z plus delta z minus f of z, that's 2 delta y plus delta x I over delta z, which is delta x plus delta y I. Now, if we approach purely along the real axis, then any delta y stuff goes away because we're not on the imaginary axis. And so we just get delta x I over delta x, which gives us I in that case. Along the imaginary axis, aka along the y-axis, we get the limit as delta y goes to 0 of 2 delta y over delta y I. And that's unfortunate. The answers don't agree. The limit does not exist. And so now the big question is, well, what is so special about f of z equals z cubed? What properties does it have for it to be differentiable, or the word that we like to use is holomorphic, aka analytic? In other words, derivatives of all orders exist. In other words, you can make a Taylor series for f of z. But what makes f of z equals z cubed differentiable, but not f of z equals 2y plus xi? And this is exactly what the Cauchy-Riemann equations answer. Now, it's all in the language of partial derivatives, so I'm assuming that you know Calc 3 up to this point. So, the Cauchy-Riemann relations say that the partial of u with respect to x, if we've got f of z, which is u of xy plus I times v of xy. If we have the partial of u with respect to x equal to the partial of v with respect to y, and the partial of u with respect to y equal to the negative of the partial of v with respect to x, that's the kind of the Cauchy-Riemann relation that isn't sufficient to say that that f is holomorphic, but it is sufficient to show that f would not be holomorphic. In other words, if these equations hold, f may or may not be holomorphic in some region R, but if these equations don't hold, then f is certainly not holomorphic in the region R. Now, what is sufficient is if that condition holds and two more. If the partial of u with respect to x, the partial of u with respect to y, the partial of v with respect to x, the partial of v with respect to y exist. So in other words, all possible partials of u and v exist, and they're continuous. So if all three of these conditions are met, then f is holomorphic in some region R. And so let's actually prove this. And by the way, just, 2 and 3 are kind of conditions that you would expect, right? Really the thing that is the crux is this first condition here. Obviously, if the partials don't exist, or if they're not continuous, or something strange or not nice is going on, you would expect the function to not be nicely differentiable in your region. But they're just worth stating for completeness. Okay, so f prime of z naught, using the definition of the derivative, it would be the limit as delta z goes to 0 of f of z naught plus delta z minus f of z naught all over delta z. And now when we expand this out, it's going to get a little yucky. So it's the limit as delta z approaches 0 of u of x naught plus delta x plus v, u of x naught plus delta x, comma, y naught plus delta y minus u of x naught comma y naught plus iv of x naught plus delta x comma y naught plus delta y minus iv of x naught comma y naught, all over delta x plus I delta y. Okay, now something that I need to mention here is that the complex derivative is what's just a special case of the directional derivative, right? The directional derivative is up to this far the most general type of derivative that we know. And so it's important to note that the directional derivative in Rn is wholly determined by at the n standard basis vectors, right? If we know the directional derivatives in the n standard basis vectors that span our space, then we know the directional derivative for any vector in Rn. In other words, I'm using the fact, and more specifically in our 2D case, that d sub u of f of a is f sub x times a plus f sub y times b, right? And f sub x is the partial of f with respect to x. In other words, it's the directional derivative in the x direction and the directional derivative in the y direction. And so what I'm really getting at is that in order to show this limit is unique, I only need to check two directions. In other words, along purely the real and purely the imaginary axis. And if those are the same, then everywhere else will be unique because of this fact that the directional derivative can be written as a linear combination of the directional derivatives in the direction of the standard basis vectors. So, along the real axis, along Re of z equals x, what do we have? We have the limit as delta x goes to 0, not as delta z goes to 0. Now it's delta x. It's u of x naught plus delta x comma y minus u of x naught comma y naught over delta x plus I times the limit as delta x goes to 0 of v of x naught plus x naught plus delta x, comma, y minus v of, x naught, comma, y naught. Oh, I forgot a y naught there. Over delta x. And that just becomes, using the definition of the partial derivatives, right? That's just partial u with respect to x plus I times partial v with respect to x. Okay, and now along the imaginary axis, which is y, we get the limit as delta y goes to 0 of u of x naught, comma, y naught plus delta y minus u of x naught, comma, y naught all over I delta y, because remember delta z is delta x plus I delta y, plus I times the limit as delta y goes to 0 of v of x naught, comma, y naught plus delta y minus v of x naught, comma, y naught over I delta y, which becomes, now notice these i's cancel, which is nice, and then a 1 over I on the bottom here on this first limit becomes a negative I in the numerator, and so we would get that this is negative I times the partial of u with respect to y plus v, plus the partial of v with respect to y. And now, in order for this limit to be unique, the limit along these two basis vector paths have to be equal. And for the equality of two complex numbers, the real and imaginary parts have to be equal. And so in other words, the real parts equaling means the partial of u with respect to x equals the partial of v with respect to y. And the imaginary parts equaling means the partial of u with respect to y is equal to the negative of the partial of v with respect to x. And with that, we're done.